Good morning. Welcome to Current Scambered. In this video, let us study valence shell electron pair repulsion theory. Okay, what is valence shell? Valence means outer shell. Okay, valence shell electron pair repulsion theory is called VSEPR theory. It is used to predict the shape and geometry bond angles in a number of covalent molecules. It is a very simple theory to predict and explain the shape, geometry, bond angles in a number of covalent molecules or ions. This theory was actually proposed by Sedgwick and Powell in 1940, okay, and developed by Gillespie and Nycombe in 1957 as VSEPR theory. Let us discuss the postulates of VSEPR theory. What are the important postulates of VSEPR theory? Okay. In any covalent molecule, there is a central atom. For example, methane molecule. In methane molecule, CH4, the central atom is carbon, around which the other atoms are arranged. The central atom is surrounded by other bonded atoms. Okay. How they are bonded? The central atom is surrounded by other atoms. The central atom is surrounded by electron pairs. Okay, each surrounded atom is bonded by sharing electron pair. Okay, so there are two types of electron pairs: bond pairs and lone pairs. For example, in water molecule H2O, there are two bond pairs and two lone pairs. What are lone bonded pairs? They are involved in bonding, that is sharing of electron pair between the two atoms. What are lone pairs? They are called unshared electron pair. They are also called non-bonded electron pair. Okay, so the geometry and shape and the bond angle depends upon the number and type of electron pairs present in the molecule, that is surrounding the central atom. The fourth postulate is the order of repulsion between the electron pairs are as follows. That is, lone pair repulsion is much greater than lone pair bond pair, which is greater than bond pair repulsion, because the lone pairs are not involved in bonding, so they are completely exposed. The electron pairs are strongly repelled. Okay, now let us see how the VSEPR theory are used to predict the geometry of 5 types of molecules. There are 5 types of molecules: AX2, okay, 1 AX2, 2 AX3, 3 AX4, 4 AX5, 5 AX6. Let us apply VSEPR theory to predict the shape and geometry of these molecules. Okay, let us take, in these molecules, they have regular geometry. These molecules have regular geometry because they have only bond pairs. You see, number of electron pairs, third column. Okay, they have only bond pair, no lone pair. If there is lone pair and bond pair, the geometry will be irregular or distorted geometry. Please remember, if a molecule has both, if a central atom in a molecule has both lone pair and bond pair, then they will have irregular geometry or distorted geometry. In these 5 types of molecules, they have only bonded pairs, no lone pairs. Therefore, they have regular geometry. Okay, let us take first AX2. For example, beryllium chloride. In beryllium chloride, as you see, Be, there are 2 bonds. There are 2 bonds. There are 2 bond pairs. There are 2 types of arrangement. As you see here, perpendicular, this is linear arrangement. This is linear arrangement. You see the structure, linear arrangement. So, the linear structure is more stable. The linear geometry is more stable because the bond pair repulsion is minimum. In this last structure, you see perpendicular Cl. So bond pair repulsion is greater only 90 degree, whereas here 180 degree. Therefore, the bond pair repulsion is minimum. So the molecule is arranged, the atoms are arranged in such a way that there is minimum electron pair repulsion. Okay, so this is the stable structure, whereas the last one, it is highly unstable, highly energetic unstable. Okay, let us see AX3 type. It has 3 bond pairs. Okay, for example, you see last column, BF3, boron trifluoride. Okay, in this, the bonded pairs, the fluorine atoms are arranged in such a way that there is a minimum electron pair repulsion. It can be arranged in T-shaped, it can be arranged in trigonal planar. In T-shaped, the 90 degree will be there. So bond pair repulsion will be higher. So in this arrangement, the bond pair are far away, there will be minimum repulsion. So this arrangement is more stable, trigonal planar 120 degree. Let us move on to AX4 type. In AX4, there are 4 bond pair, 0 lone pair, this CH4. Let us consider, for example, CH4 molecule, and the bond angle is 109.5 degree. In tetrahedral arrangement, the bond pair repulsion is minimum. Okay, so the geometry, the preferred geometry is tetrahedron. Next, AX5, there are 5 bond pairs, 0 lone pair. For example, PCl5, the geometry is trigonal bipyramid. Okay, in this geometry, valence shell electron pair repulsion is minimum because there are 2. See, this is axial bond and equatorial bond. Okay, axial you have 90 degree and equatorial planar, okay, like trigonal planar 120 degree. Okay, next AX6 type. There are 6 bond pairs. The geometry is octahedral. For example, SF6, the bond angle is 90 degree. In this geometry, the bond pair repulsion is minimum. So this is the predicted geometry based on VSEPR theory. Okay, so far we have considered only bond pair, the molecules with only bond pair. Let us consider molecules with the bond pair and lone pair. Okay, now let us take the first type. In first type, AX2E0. What is E? E refers to number of lone pair. See here, E refers to number of lone pair. E0 means there is 0 lone pair. This is again linear molecule 180 degree, and the central atom is sp hybridized. Therefore, the geometry is 180 degree. In this, only one type is possible. Okay, let us see the AX3 type now. Okay, let us now consider AX3 type molecule. In the first case, without lone pair. Okay, so this is again we have already discussed. Next, let us substitute one bond pair. One bond pair is replaced by one lone pair. Therefore, AX3 becomes AX2E1. Okay. Now, example SO2. In SO2, there are two bond pairs and one lone pair. Okay, CO2 is a linear molecule because they have lone pairs, bond pair only. In SO2, it is not a linear molecule because it has one lone pair. Because of this, lone pair bond pair repulsion is greater. Okay, therefore, this is the bond angle is contracted, shrunk. Okay, therefore, instead of 120, both are sp2 hybridized. Instead of 120, the bond angle is 119 degree because of lone pair bond pair repulsion is greater. Therefore, the bond shrinks, bond angle shrinks. Okay. Okay, let us move to AX4 type. In the AX4 type, okay, without lone pair, that is AX4E0, that is example CH4 tetrahedron 109.5 sp3 hybridized, we have already seen. Now let us replace one bond pair by one lone pair. Therefore, AX4 becomes AX3E1. So this is example ammonia molecule. Ammonia molecule is the central atom is bonded to 3 hydrogen atoms NH3 like AX3 and one lone pair. This is again sp3 hybridized because of lone pair bond pair repulsion, which is greater than bond pair repulsion. The geometry becomes, the bond angle is becomes smaller. Okay, 107.3 because of repulsion between bond pair lone pair, and the geometry is trigonal pyramidal. This has pyramidal geometry. Next, another lone pair, another bond pair is replaced by lone pair. Therefore, for example, water molecule, this is an example of water molecule, is a suitable example of AX2E2, and here you see there are two lone pairs. So lone pair repulsion is very much greater. As a result, the bond angle is very much smaller, that is 104.5 degree, although it is sp3 hybridized. Okay. Okay, let us now consider AX5 type without lone pair, only bond pair. This is a regular geometry because there is no lone pair. PCl5 example, this is trigonal bipyramidal geometry, sp3d hybridized. The central phosphorus atom is sp3d. It has both axial and equatorial chlorine atoms, therefore 90 degree, 120 degree bond angle respectively. Let us replace one bond pair by one lone pair. Therefore, AX4E1. Example SF4, okay, and the geometry is seesaw. In this arrangement there is minimum electron pair repulsion, seesaw arrangement. The bond angle is 86.5 and 102 degree. Let us replace another bond pair by lone pair. Therefore, AX3E2, for example, ClF3 it is a T-shaped molecule, okay, because of lone pair repulsion is greater. They are all sp3 hybridized, and the bond angle is this linear. One is linear, one is mutually perpendicular, 90 degree and 180 degree. Okay, let us now again replace one bond pair by lone pair. Then AX2E3 and AX2. Therefore, the example is XeF2. It is a linear molecule because of 3 lone pairs. In this arrangement, the molecule has less energy and more stable. Therefore, 180 degree. Okay, let us see the AX6. This is the final type, AX6 E0. That is, it is a regular geometry, octahedral SF6 sp3d2 hybridized. The central sulfur atom is sp3d2 hybridized. The bond angle is 90 degree. As you know, for octahedral geometry, this is the most stable arrangement for octahedral AX6 type of molecule. Okay, let us now replace one bond pair by one lone pair, AX5E1 BrF5. See here the structure, you see last column, there is one lone pair. Okay, so the geometry is square pyramidal and the bond angle is 90 degree. This is irregular geometry, distorted geometry because of lone pair, because of the presence of the lone pair. Okay, this is the only one type possible for this AX65. Thank you for watching. Please share and subscribe. Thank you again.